Today's lesson is going to focus on energy and work. Let's take a look at the history really quickly before we get into the actual problems that deal with it. You won't have to know the history, but it's just somewhat interesting for us to take a look at. In about 1850, energy was invented. The reason why physicists started taking a look at energy and talking about different objects and how their energy was because it provided an easier way to do problems. This man is one of the two scientists who actually was highly involved in this process. This is James Joule, and we're going to see that he is one of the guys whose names is used for our units. The second guy is what I consider pretty happy. He was James Watt. His picture, we'll see in a second, does not show a very happy face. Joules are our unit for energy because of James, and James Joule, and watts are going to be the unit that we use for power. We're not going to get into power in this PowerPoint, however, we will be talking about that later within the unit. But again, energy and the way in which we talk about energy was simply an easier way to talk about a problem. But what is energy? Well, energy is the ability to do work. Now, we talk about work all the time. We do so much work. So what is the physics definition of work? Well, the physics definition of work is a change in energy. It's very circular. When an object has energy, it can do work. When work is done to an object, it changes the object's energy. So we have to kind of take a look at some of these things. We're going to start first by taking a look at what work is. Work involves force. In order to do work, you are going to have to apply a force, just as this guy is trying to apply a force to the barbell. The amount of force is going to be directly proportional to the amount of work done. So basically what we're saying here, my pen went away. What we're saying here is that work is directly proportional to the amount of force that's being done. That's not the only thing. In order to do work, we also have to involve a distance. The object has to move, and work is going to be directly proportional. Work is going to be directly proportional to the amount that the distance moves as well. So we're going to take these two and put them together. I would make sure to write this equation down. Work here, which, sorry about this, guys. Keep forgetting that the pen disappears after every slide. Work, which is going to be measured in joules, is equal to force, of course measured in newtons, times distance, which would be measured in our meters, times the cosine of an angle. Now, this is the cosine of the angle at which, in between the force and the distance. And basically what this is telling us is that in order for work to be done, we have to see that the force is directed in the same way as the distance. We're going to take a couple looks at examples that involve this. For the most part, we are going to be focused on this first half of the equation. And the second half is simply a conceptual thing that we're going to be working with. But I like to include that in our definition right now so that we can kind of keep that in mind as we go about these different problems. So, both force and distance must be in the same direction. That's the cosine theta from the last part of the equation. This is what that portion is talking about. An angle force only makes up a component of it. Again, that's your cosine theta part. And we're going to see that work can be negative. So let's take a look at some examples. Okay, in this situation, we see that there's a force being applied here, and that force is going up and to the right. The motion is simply going to the right. So in order to figure out how much of the force is actually adding up, or what part of that force we would use for the work, we would simply look at this as though it were a vector, because force is a vector. And in order to go through all of this, we would simply say that Fx times distance would equal our work. And if we would put in whatever that angle was, we would see that Fx is simply equal to F cosine of theta. Okay? In this case, since the force and the motion, force X and the motion are both going in the same direction and they're helping each other, this is going to be an example of positive work that is being done. Right? We'll move on to our next example. Example number 2 here is going to be a situation where we see negative work is being done. Because in this case, we are going to see here that we have our force in the x direction. Again, that's the only force that's going to be mattering because that's the one that's in the same plane as our direction of movement, is going to the left, whereas our distance is going to the right. In this situation, we would see that we have a negative work that is being done. This could be something like the wagon here is rolling towards you, it's moving towards you, and you try to go to stop it. You are going to be doing negative work to this actual object. In example 3 here, take a moment, hit pause, and see if you can figure out if it's positive or negative. When you have your answer, you should see that since Fx is going to the right and motion is going to the right, this is positive work. In the second to last example, we're going to see the direction of force is up and to the left. Their direction of motion is to the right. Again, hit pause, see if you can figure it out. In this situation, I'm going to say f of x is to the left, distance is to the right. Since they don't line up, this is going to be negative work, or since they're going directly opposite of each other. Again, I care about f of x because that's the part that's parallel to my direction of my motion. And work is looking at the force that's actually causing it to, or the amount of force it's actually causing it to move in that direction. And our first force in the y direction is not helping it move to the right or to the left. In this fifth example, we see something kind of strange. This could be a situation where maybe you're holding this cart up and you are moving to the right. Your force is going directly up. Your motion is going to the right. There is no f of x. So there's going to be no work done. Another way you could think about this is the angle between the force and the distance is 90 degrees. If we plug back into our original equation where we had the cosine of 90 degrees, work equaled force times distance cosine of angle, cosine of 90 equals 0. So anytime you see the force is perpendicular to the direction of motion, no work is being done. It's kind of a strange concept, but it's something that you need to keep in mind. In order for work to be done, two conditions must be met. The object must move. Even if I were to stand against a wall and push and push and push and apply a lot of force, the distance that the object would move would be 0, and therefore my work, which equals force times distance, would also equal 0. If it doesn't move, there's no work. The second is that the force must act on the object in the direction that the object moves. Again, we are looking for the component that's going to be parallel to the motion of the actual object. If force is perpendicular and motion to the actual motion, then no work is done. In this situation that's coming up on the actual board here, you are going to see in this case we would only take one of the components. This mom has picked her child up from an angle, and she's moving the child, so we would only care about the direction that she was moving the child. Uh-oh, spinning wheel. Why is my PowerPoint freezing on me? Sorry about this, guys. We'll pause the video for a second.